This section discusses some of the benefits of drivers and specifically why people frequently choose drivers instead of Skippy when they're architecting their systems. It's helpful to look at an example here of programming with both Skippy and how things are programmed in C. So if you look at the two green boxes here, you can kind of see a little bit more about what's going on. In the case of Skippy, a typical operation is we're just going to measure a DC voltage. So from Skippy, you would, using a library like Visas in the string, measure volt to the instrument, and you would format into that string the range and the resolution that you wanted to measure, and then you turn around the bus and get a reading back from the instrument. So it seems simple enough. It's reasonably abstract, and that you don't have to deal directly with the instrument significantly. One of the things to notice in this case, though, is that the application program is dealing with the strings that are being sent to and from the instrument. So if you have a syntax error, say you've got a comma in the wrong place, or you include one too many semicolons, that syntax error is going to be caught by the instrument when the system is run and the string's actually sent to the instrument. And in order to be able to check for errors in your program, the application program, well, you're going to have to look at the instrument and see a little red light come on in front of the instrument and say, I got a syntax error. Or your application program has to go off to the instrument, read an error queue in the instrument, and report back that something went wrong. So none of that's disastrous, but that's kind of a natural part of controlling an instrument by sending strings to it. It's a very simple model, and one of the most attractive things about the model is that there's nothing to install on your computer except for whatever library allows you to send strings and read strings from the instrument. So that simplicity of the install and the structure on the client computer is one of the biggest benefits there. You know, just to contrast with that, with a driver, I mean, the syntax I've used here is IVC, but I mean, we could talk about the same thing in C# or LabVIEW. It's a very similar customer experience, whichever language you use. But if we just look at this from C for a second, you know, you've got something which from a abstraction standpoint really looks a whole lot like we had before. We're saying we want to measure DC volts. We're specifying a VI, which is the connection to the instrument. We're specifying a range, which is of course a variable here and a variable here, specifying a resolution. And with the driver, we're going to go ahead and get the reading back in one call. It was one more line of code for Skippy, but that's hardly something that a professional programmer is going to find daunting. I think the real differences here are more what's described here, and that is, in this case, we're really, from the perspective of the program, sending those program variables directly to the instrument. There's no chance for a Skippy syntax error there because we're using the syntax that's implicit in the programming language we're using. Anything like a syntax error, if I forget a comma in this string or put a semicolon in the wrong place, I'm going to get a syntax error from my compiler when I compile the program. I don't get the error when I run the program and it talks to the instrument. Now, if you always write your programs with an instrument directly connected to the computer, that's not a big deal. But as you look at developing programs without the instruments being present, this becomes more and more important. Another potential advantage of this driver interface is you avoid the performance impact of doing string manipulations. Now, clearly, modern computers can do string manipulations extremely quick, but things like floating point number builds and some of the ASCII parsing is something which can begin to take a noticeable amount of time for really high-speed operations. Another advantage of the driver is that you're using debug tools and techniques that the programmer knows. So whatever tools the system designer has for debugging a problem and single-stepping and debugging their tool, this is just a subroutine call. So whatever they want to do to, put a watch on the range variable or do tracking or tracing and so on, is going to work really just the same with the tools they already know, because it's a function call to a function just like they've been using in the rest of their application program. Whereas in this case, I've got a string that's going out to a separate instrument, separate device, and I've got all the challenges of dealing with that. So what you can see here is that the abstraction, the way you express what you're doing, ends up being very similar between Skippy and C. Now there are occasionally some differences there also, but the simplicity in putting the system together, debugging the system, and potentially performance of the system can be different between the two. So that's why the drivers are frequently used instead of Skippy, and why as a consortium we think it's important to have a driver solution as well as the Skippy solution. To talk in a little more detail about what IVI drivers are, the IVI specifications are in two groups that occasionally causes some confusion. One group is these architecture specifications, shown here pictorially at the base that the other things are built on. And there are numerous architecture specifications, and you can see the reference to those specifications is always 3 dot something. These are the specifications that describe basically how do you build a C driver, how do you build a COM driver, how do you build a .NET driver, and exactly what that looks like, how it's installed, common functions, how to generate mnemonics, how to work in the various software environments. So that ends up being a lot of work, especially for the variety of languages that are supported. And so there's about a little over 1,000 pages of specification there, which are fairly significant. This number is actually a couple years old. This may have grown by a little bit. But there's a distinct set of specifications, which is more important than the page count, that really talks about the behaviors of specific instruments. And so these are the specifications that begin with a 4 dot, and they describe standard interfaces for common classes of instruments. So there are about 13 different specifications. Each one of those specifications is a couple hundred pages, and it's really, this is the standard set of calls that a digitizer uses, this is the standard set of calls that a counter will use, or a spectrum analyzer, and so forth and so on. And these are specifications that an individual instrument driver could comply with based on the type of instruments controlling. The architecture specifications are specifications which are generally required of all drivers. And as a matter of fact, there are lots of drivers that control instruments that aren't fully described by these 13 specifications. It's really only relevant for them to comply with the architecture specifications. We'll talk some more on some of the later slides, but there are substantial benefits to complying with the architecture specifications beyond just the obvious benefit of complying with the class specification. Clearly, the reason the class specifications are interesting is you would like to be able to build a system that controls a DMM and have that not be specific to a particular DMM. And so having the class specifications provides a common set of APIs that are implemented by instruments of a class, and it simplifies the work of somebody maintaining a system. They need to put in a different piece of equipment. One thing that's important to realize there is that there are capabilities of different pieces of equipment that are described that are more involved than what just shows up in the API. So clearly, you're not going to be able to take a $5,000 10-year-old spectrum analyzer and replace it with a $250,000 brand new vector signal analyzer, even if the vector signal analyzer implements a spectrum analyzer interface. There are things that it does in quality of measurement, types of measurement, that don't fit the same. But where the instrument is working in that kind of common set of capabilities, it's very convenient if it will control those things the same way. So, a little more information on the IVI architecture specifications. There are 3 different types of specification in that 1,000 pages that I alluded to on the previous slide. There are the C DLL standards, which really are useful for lots of programming environments that are able to call a general Windows DLL, but we really think of those primarily as being C standards, so that's what IDC refers to. The IVCOM standards, and again, any application environment that can call COM works well with those COM components. The primary use we see for those is .NET development environments. And then finally, there's a set of standards around .NET, and these .NET assemblies are also primarily for .NET environments, but can be used by other tools that call .NET assemblies, and there's a few of those also. Turns out the COM architecture was done before the .NET architecture because that's just a technology that's been around a little bit longer. So the provides a excellent usability when you're using a .NET development environment. The .NET standards provide some extra capability that makes the drivers a little more convenient to use in .NET, a little bit more object-oriented, just because they're more intrinsically based on object-oriented technology. Each one of the architectures, C, and .NET, make use of the same class specifications. So that list of classes that were supported, DBMs and digitizers and things like that, is equally applicable to all of the IVI architectures. But each architecture has its own rules for installation and style and things like that. It really goes a lot deeper than just installation and style, and that the basic structure of the driver and how it's managed ends up being a little bit different between the architectures. There'll be more on the difference in the architectures in a later section. Another important aspect of IVI, and one of the benefits of the driver standards themselves, is the fact that there are a substantial number of common components that are made available with the drivers. By common components, I mean specifically things that are provided by the IVI consortium that have been contributed by one member or another, or maintained by one member of the consortium or another, that are really helpful in enabling multi-vendor systems. One of the things you run into when you look at customer issues around common drivers is that there are some common APIs, some common definitions that you really need. The first bullet here on the list, the C shared components, is a great example in that there's a common need for a definition for things like infinity and some of the basic programming operations, so that you can deliver all those DLLs and use them all together in one customer application. It's not a big technical problem, but things need to be provided that are consistent and work well. So there's a set of C shared components. There are also floating point services. There are also tools really dedicated towards common.NET. There's the Session Factory, which is a tool that allows you to abstractly open a session up with the instrument based on some system configuration. And there's more information on how to use that in a later session. And there are the necessary publisher pieces that permit real true polymorphism. In the .NET world, you have to have a common publisher of that common format, or that common interface that all the drivers implement, and that's included there. So when we talk about compliance of IVI drivers, as you can see from a couple of slides ago, that there are the architecture standards and the class standards. It's important for somebody that's picking up a driver to use it to be able to understand what are they getting and what it does. So IVI compliant really means, as a term, that the driver complies with those architecture specifications. So that means that they have a common behavior model, they support common IVI features. Again, there's another slide talking about those features. I won't dwell on that now. It means that they have an install that's standard and works with the others. That's pretty important because you want to make sure that all of your DLLs or .NET assemblies or whatever piece it is you have are installing consistently so that you can find all the pieces and they all sit alongside each other as you would like them to, and not in some vendor-specific solution. And then there's a common API for some common tasks. So there are common functions that are implemented by all IVI drivers. Again, this is just aspects of that common architecture. Another thing that's extremely valuable and sometimes we overlook is just the benefits of having a consistent API. Knowing that the API is going to be organized the same, make use of the hierarchy the same, have similar data types is all of real value when you go to put together a system and you're integrating software components that come from several vendors, because obviously a system is typically made up of instruments from several vendors, and that means that the software is coming from multiple vendors, and to have that work alongside each other and be consistent. And little things like the way mnemonics are generated, names for parameters, names for functions, can be infuriating when things are just done completely different from driver to driver. So having some of that consistency that's driven by compliance with the architecture is really valuable. So when we talk about an IVI compliant driver, those are the sorts of capabilities we're talking about. Definitely substantive benefits, but not all of the benefits that you get when you talk about a class compliant driver. So a class compliant driver adds to that the driver complies with that instrument class API. So that means that the instrument's been identified as being one or more of those types of 13 of classes. You're a digitizer, or you're a scope, or you're a DMM, or a arbitrary waveform generator. And there may still be some custom API available, because clearly there are instruments that do more than what's in the common API, but the standard API is there. And again, that's the key piece to really simplify exchanging instruments. So it's not going to make all instruments look exactly the same, but it's going to give you a great step forward when you go to deploy or update an instrument in a deployed system to one from a different model or a different vendor or something like that. So just a couple slides here just talking about why we think IVI is important and valuable to people doing systems. So if you look at just using the driver in the system, having that uniform way of doing common tasks that I kind of have alluded to already. So all the drivers are instantiated the same way, they're all initialized the same way, they're shut down the same way. You've got that common control of features, as I mentioned. The configuration and installation is consistent. There are registry entries that allow you to discover what drivers are on the system, and being able to open and close and query that information in a standard way is very beneficial. There are also, one thing that we see a lot is multi-channel devices, and having a standard way of dealing with multiple channels, whether it be a 2-output arbitrary waveform generator or a 4-output power supply, or just a oscilloscope that has 3 external triggers and you need to deal with those 3 external triggers. Having a standard mechanism for that repeated capability is very beneficial. And error reporting is also a clear benefit in being able to get errors consistently from all the drivers on the system. So a lot of simplicity and use there, of which the class compliance is just a part of. Another benefit of IVI is common features, capability that you know you can count on from all of your drivers. Broadly across IVI, really those first 4 bullets are key. The syntactic interchangeability you get from common classes. Simulation is probably one of the most valuable things that you can count on an IVI driver. That is the ability to run the driver without the instrument being physically present. So it's extremely beneficial if you're developing your software on something other than the computer with the instrument attached that you're doing the program for. It doesn't provide complete simulation of your system, because obviously when you want a system to work without a device present, you'd really like to know something about what is the voltage that the DUT is generating at this point. So that's really beyond the scope of what can be done with driver simulation. But having the drivers able to step out of the way and provide that simulation solution, even if it's not providing measurement values that are relevant to the DUT that you're going to have attached, having the driver just function without the instrument attached, having all the calls work and behave correctly is very beneficial. Another common benefit is fine-grained control through properties. One of the common concerns about drivers is I make this driver call and it changes these 5 things and it takes too long to execute, and all I really wanted to do was change a particular setting by 1%. You want to change the range. You want to change the output voltage by a millivolt without changing everything else. So one of the common patterns in IVI is this every function call that has a bunch of parameters. You can also adjust each parameter individually by using what's called properties. So it's a very common object-oriented paradigm, but it's been extended through the .NET COM and C drivers to have independent access to each of those properties. And of course, broad benefit of IVI is that these drivers are usable in many development environments, and some of the validation that's necessary to make sure a driver is going to work in a given development environment is kind of taken care of, because this driver does comply with the standards. So it uses data types that your development environment understands. It uses other aspects of the development environment. It doesn't have any peculiar requirements. Shaded on this slide in green is something which is new with IVI 2014, and that is one of the things that we realized as a consortium. There were several things that were common to many of the drivers, but they weren't guaranteed by the specification, and customers were concerned that they would get a bunch of drivers and there was a little bit of inconsistency in the features that were provided. So we went through and made into IVI requirements effective in 2014 some additional capabilities which aren't really beyond the scope of the earlier drivers, but they weren't guaranteed by compliance to the standard. So if a driver says it complies with IVI 2014, you also have these things. So that includes each driver that's built on top of Skippy or a Skippy-like interface has to document the commands that are used by each function. That can be really beneficial if you need to be able to look at the documentation or look at a parallel program that was done in Skippy to understand what's there. Drivers are also required to support direct I/O, and again, this is really limited to drivers that are based on an interface like Skippy, but the driver itself provides a way if you need to do something that's beyond the scope of the driver, or maybe it's just a small adjustment that's not available through the driver. The direct I/O guarantees that the application program can reach in and change individual settings by sending native language commands to the instrument. So key thing for direct I/O is it provides a way to send those native language commands. I mentioned before one of the benefits of IVI up here on the second thing was fine-grained control through properties. Well, there's now a rule that says for all function parameters, you have to provide those properties to get that fine-grained control. So now there's a guarantee to people using drivers that they get that. So in addition to just having the technology in the driver architecture, there's a requirement. Another requirement is that there be source code for the drivers. And again, as was true of the Skippy bullets above, this is really limited to instruments that are built, it's limited to drivers that are built on top of another interface. And Skippy is normally what we think of there, but it could potentially be other things. But if there's another documented interface for the instrument, you're required to provide that source code. And there's also some required consortium testing. This is something that the consortium was reticent to put into a standard originally, but there'd been enough concern about the quality of some of the drivers that were out there just from a limited set of vendors, we wanted to include a requirement that there be some testing that has been guaranteed before a customer picks up a driver, tries to use it. So again, several of these things, certainly the testing bullet was something that many, or I would say most of the vendors of the drivers have been doing all along, but since it wasn't specifically a required rule in the standard, there was no way to go to a vendor or a driver and say, you don't comply with the standards, you've got to stop using the IV mark. Now that we've made that a part of the standard, we've got a little bit more to work with there. Another basic benefit of IV is that, and to some extent this is a benefit to the instrument provider more so than the customer, but it is definitely a notable benefit, and that is by complying with these standards, you really made sure that the driver works in a broad variety of development environments. Now, obviously, the .NET COM and C drivers will work in somewhat different environments in different ways, but we've been very careful with the standards and the architecture standards to make sure that all of the necessary rules and restrictions are in those to make sure that the drivers work in the development environment of choice. So obviously, listed here things like the Visual Studio environments, the National Instruments environments of Lab Windows and LabVIEW, MATLAB, Agilent V, all of the test measurement providers have been involved in the standard and ensured that their tools work with the drivers. And for our part, we've looked at the Microsoft standards, Microsoft environments, I should say, to ensure that the drivers work well in them as well. So having a driver that will work in any development environment is extremely compelling for a instrument vendor that needs to provide a driver or a set of drivers for all of their customers. From a customer perspective, it's awfully nice to know that if you get a driver and your system is composed of some legacy C code, modern C++ code, and maybe there's some .NET code in there also, or some LabVIEW portions, knowing that you can take a single driver and incorporate all of those different test languages is beneficial from that perspective also. One more thing I'll mention as a benefit of IV is the fact that there is a IV registration page. So any IV compliant driver has to have an entry on the consortium registration page. That means customers that are off looking for drivers for a particular instrument have a place they can go to, and there may be multiple drivers for a given instrument, but anything that's IV compliant will be registered and documented there so that you can find what you need. So obviously there are hundreds of drivers listed there, and it's beneficial to both detect them, and in the unlikely event that there are issues with the driver, this is kind of the first step in identifying a specific driver that may or may not have an issue. And obviously if there are problems with the driver, it gives the consortium a clear mechanism for eliminating a driver from that registration page if it's not complying with the standard and there have been customer issues with it. This section describes the IV foundation itself and the specifications that it works with and some of their interaction with the other specifications. The primary purpose of the IV consortium is expressed here from the IV Foundation bylaws, and that's to promote the development and adoption of standard specifications for programming test instruments. That's a fairly broad charter and reflects the consortium's involvement in things from basic instrument I/O up through high-level programmatic interfaces for instruments. This illustration shows several of the specifications that govern how modern instruments are put together and communicated with. And I want to start here looking at the Skippy specification over on the left. It was originally developed with an understanding that it would need to be applied to other interfaces. but it was primarily done with GPIB in mind, and as such the Skippy specification takes the IEEE 48 and 48.2 standards and builds directly on top of them all the way to the highest levels of the interface. So the abstract Skippy instructions provide pretty high level access for how a measurement's made or how stimulus is generated from an instrument. And the standard really has everything from that high level description of what the instrument is supposed to do down through the interface to GPIB as all part of that one standard. In order to be able to apply Skippy to things like USB instruments and Ethernet instruments, other standards have come along, including USB TMC and high-slip and VXI11, both of which typically are used on top of LXI to get to Ethernet instruments. And so Skippy's been applied to other interfaces, which is very helpful because Skippy's a nice standard, but also it allows systems built with GPIB instruments to also communicate over Ethernet and USB. That really gives rise to another aspect that you can see in looking at these standards, and that is across the bottom here in purple, what we have are, with the exception of GPIB, very conventional computer standards that really provide the physical connection to the instrument as well as the delivery of data to it. And then we have test and measurement standards in every case that are built on top of those common computer standards that provide the extra capabilities that are needed to build a test and measurement solution on top of them. So that's why we have things like LXI for accessing Ethernet, USB TMC for TMC, VXI really originally targeted at VME has been extended now to PCI, and of course PXI and AXIE as standards that are built on top of PCI and PCI Express. So basically this row is showing that, and again, with GPIB, everything was designed for test and measurement and provided what was necessary. So you can see here at the next layer in that communication stack, high-slip and VXI11 providing ways to access Ethernet instruments. Most new instruments now are probably being built with high-slip, which provides higher performance, lower latency communication than VXI11 did, just because it's built on top of some more current Ethernet technologies than VXI11 was. And things like the PXI2 and PXI6 software specifications, which are really part of PXI, provide some of that software layer on top that really delivers the basic communication that's needed to build more on top of it. The VISA, most people are familiar with, is a common library for accessing the instrument I/O. So software applications are able to look into VISA and see all of these different I/O interfaces very similarly. So the application doesn't have to worry too much whether it's talking to a Skippy instrument on GPIB or a Skippy instrument on Ethernet or USB, or whether it's talking to a register-based instrument on any one of the various register-based interfaces. The next layer that's really described here, and you can see it's kind of a natural built-in part of Skippy, is the layer that provides the programming interfaces to the instrument. So things like C and C++ and C#, Visual Basic, LabVIEW, all have different needs for a software instrument driver to work on the system. Finally, on top of that, there are the IV instrument standards. There have also been VXI plug-and-play instrument standards, but the focus of the IV class standards shown here is really specifics of how calls are made to specific types of instruments, which is provided by IV class specifications. We'll talk more about the structure of the IV specifications in a minute. One thing that's important to realize is that as we look at these standards, all of those that are shaded in blue on this slide are the ones that the IV Consortium is responsible for. That is, they own the intellectual property and the standards themselves. So although some of this work was done under the auspices of other organizations through the years, it's all been transferred back to the IVI Consortium for a more natural place, because there's enough similarity and synergy between these standards. It makes sense to have all of that management of the work in one place. So even for standards that are reasonably stable, don't have very much active going on, like Skippy, it still has to have a consortium behind it that's backing that up, owns that intellectual property, and maintains it. This next illustration is trying to show a little bit more about how some of these specifications relate in terms of requirements. So we've already said that Skippy is built on top of GPIB and LXI. The IVI driver standards themselves really provide you access to instruments, whether they be Skippy instruments on GPIB or an LXI instrument, or a VXI, a PXI, or an AXIE instrument. So one of the things to notice here is that the IVI standards as a higher level driver standard really describes the instrument interface in a way that lets you access instruments on any of the common instrument interfaces, making use of some of the other standards in the stack. And as a matter of fact, both the LXI standard and the AXIE standards require that instruments provide IVI drivers. In the case of PXI and VXI, both of which standards preceded the existence of the IVI Consortium, they require that drivers be provided, but VXI plug and play as an earlier generation of driver is also acceptable and appropriate for them. That covers the basic description of what the IVI standards are and how they relate to one another.
Thank you for your interest in this IVI training video. There are several other videos available on the IVI Foundation website, along with Getting Started guides and Getting Started videos. All are available at the URL here, http://www.ivifoundation.org/resources. Thank you.